the boundary layer equations provide us a tool to analyze the viscous effects contained into the boundary layer and estimate the friction and the drag acting on the surface. In this lesson, we are going to analyze different methodologies that have been used to extend the range of applicability of the boundary layer theory. The different approaches will give us a set of equations that we can use to study different cases, such as non-constant mean flow, non-zero pressure gradient, corrections for low and high Reynolds number, solutions for geometries different than the flat plate, and three-dimensional flows. We have several methods to study, so let's get started. We can extend the range of applicability of the boundary layer equations to the case on non-constant mean flow, meaning that the free stream velocity can vary with x and time. We can then recast the equations into this form, where the terms in the bracket take into account the pressure gradient. This expression of the boundary layer is valid for both laminar and turbulent boundary layers. Starting from these equations, Karman came up with a form of the momentum integral equation, multiplying the continuity equation by the difference of the x component of the velocity and the free stream velocity. Then he subtracted it from the momentum equation. In the integral form obtained, we can recognize the expressions of the momentum thickness and the displacement thickness. The term Vw is the normal velocity to the wall that takes into account injection or suction of air through the wall. Substituting the momentum thickness and displacement thickness terms, we can rewrite this equation in this form and connect it to the skin friction coefficient. Under the assumption of steady flows and non-porous walls, we can reduce the expression to this form, where h is the shape factor. This form of the Karman integral relation is used in the analysis of turbulent boundary layers. Now, starting from this equation, we can introduce the correlation method of THWAITES to develop a solution based on correlations that works for non-zero pressure gradients and up to the separation point. The idea is to multiply the Karman relation by a factor and defining a correlation parameter lambda to develop a new form of the equation. We can see that the equation can be written in this form, where we can identify some correlation functions. One is the shear correlation, and one is the shape factor correlation. We can wait. Okay, so let's step back for a moment and understand what we mean with correlations. Back in those days, numerical techniques were not available or extremely popular, and scientists could rely mostly on experimental data to understand physical phenomena. In this regard, many of them started trying to understand how different variables can correlate with specific behaviors and better understand what parameters affect a specific kind of physics. Correlations were found after intense studies of extremely large amounts of experimental results to identify specific patterns that can lead to mathematical models that we can use to describe the flow. Going back to the analysis, we can rewrite the equation in terms of these correlation functions. THWAITES found that for a large set of experimental results, the f function could be described by a simple linear fit. Substituting this expression into the ODE, we can finally solve it and obtain an estimate of the momentum thickness that we can use to calculate friction and drag. In this particular expression, the constant c is typically set to 0 to avoid theta to be infinite when the location x0 is a stagnation point. The final quadratic relation for the momentum thickness gives us an accurate prediction of the data within 5% for favorable or mild adverse pressure gradients and within 15% near separation points. We can also estimate the shear stress and the displacement thickness once we know the momentum thickness, using the following expressions, where we can use a curve fit for the shear function and a polynomial form for the shape factor function. The next method that we are going to analyze is the Falkner-Skan equation. This is a similarity solution approach for flows over wedge-shaped geometries. They generalize the Blasius solution for variable free stream velocity, and then they found out that if the velocity has a power law distribution, a similarity solution can be obtained. The non-dimensional coordinate eta is different compared to the one used in the Blasius solution. Combining this equation and following steps similar to the one done for the Blasius solution, we can obtain this single ODE that describes the boundary layer over wedged shapes as long as the boundary conditions are satisfied. Wall as a streamline, no slip condition at the wall, and free stream velocity at infinity are the boundary conditions that we need to include. In the expression, we have a beta term that appears. This term represents a measure of the pressure gradient in the flow field and is connected to the angle of the geometry. With this in mind, we can have special cases such as a flat plate and a vertical plate. The Falkner-Skan equation includes the effect of the pressure gradient in the solution. The gradient can be calculated using Bernoulli's equation from the free stream velocity. The solution of the equation is similar to the Blasius boundary layer, except that a numerical integration method is required to obtain the solution. The equation relies on the parameters beta and m. So let's analyze now the physical meaning of m. If m is less than 0, the study case presents an adverse pressure gradient, meaning that the pressure increases along the flow stream direction. The pressure change along the surface acts as an obstacle, slowing down the fluid, or even reverting the fluid direction and creating separation. If m is larger than 0, we have instead a favorable pressure gradient. Hence, the pressure decreases along the flow stream direction, and that helps the fluid stay in contact with the wall. Different combination of beta and m can represent different configurations, such as expansion corners and wedges. Here we can see the predicted velocity profiles for different combinations of m and beta terms. As you can see, the profile shape can vary significantly, and for the red profile we reach flow separation. The Falkner-Skan equation gives us a good prediction that takes into account pressure gradients and is valid up to the separation point for different geometries. The boundary layer equations that we have seen so far deal with two-dimensional flows. But we can also extend our analysis to three-dimensional boundary layers. Consider a plate aligned with the xz plane. We can write the 3D boundary layer equations in this form, where u infinity and w infinity are known free stream velocity components. Three-dimensional flows can also present cross flows that affect the velocity distribution in the boundary layer. Cross flows are typically referred as secondary flows, since their magnitude is generally smaller than the intensity of velocity in the main flow direction. Examples of secondary flows in boundary layers can be aircrafts with swept-back wings, or cross-flow on turbomachinery blades or propellers. If we look at the distribution of velocity along the mainstream direction, we can identify our typical boundary layer profile. If we then include the components of velocity acting on the plane normal to it, we can see that they are not zero for secondary flows. And we can have a unidirectional skewing or a bidirectional skewing. In the example presented here, we have a duct with an S-bend that generates a secondary motion in the fluid. The analysis introduced up to here are based on the assumption of thin boundary layer and relatively large Reynolds numbers, with a limited range of applicability. The boundary layer problem has a singular perturbation nature, so if we introduce the non-dimensional form of the boundary layer momentum equation and take the limit of Reynolds to infinity, you can see that the term on the right-hand side vanishes. This creates a singularity where the equation cannot satisfy anymore the no-slip condition at the wall. However, even for large Reynolds number, we actually have no-slip condition at the wall. Hence, the boundary layer theory is not physical for extremely large Reynolds numbers. Friedrichs approached the problem to correct this limitation, and successively Van Dyck introduced an asymptotic methodology to provide a complete solution. Following Friedrichs' approach, the boundary layer momentum equation can be roughly approximated by this ODE and its respective boundary condition. The equation can provide us two different solutions for two distinct regions. One is the inner layer dominated by the viscous effects, where the no-slip condition must be satisfied. The second one is the outer layer, where we are approaching the free stream velocity and the viscous effects are limited. The two solutions are valid only in their respective regions. Van Dyck introduced the matching principle. The idea behind it is to blend the solutions of the two regions to create a composite function that represents the entire region. Shown here is the first-order analysis of the physics model for the inner layer and the outer layer. We can see in the plot that they are disconnected. Blending those two functions, we can obtain a description of the entire profile. Van Dyck further extended and generalized this first-order procedure into a matching approach for inner and outer expansions of any order. This methodology has been used to correct leading-edge effects at low Reynolds numbers and trailing edge effects. As an example, reported here is a second-order asymptotic correction for the flat plate boundary layer. The final result for the drag coefficient is a sum of the Blasius solution and the second-order correction term. This let us extend the Blasius solution to the range of Reynolds numbers between 1 and 1000. The matching principle is widely used also in the analysis of turbulent boundary layers. In this lecture, we have seen different methodologies that have been used in the past to extend the range of applicability of the boundary layer theory to predict friction and drag for a wider set of phenomena. Effects like the presence of pressure gradients, three-dimensional flows, low and high Reynolds numbers, as well as non-constant inflow conditions, can in this way be analyzed.